This is we talk about the Aviles-Giga function this, and but I will skip the things that are already been said. So it's about the thing here, the difference that we consider a non-oriented version of the Aviles-Giga function. And it's John work with Michael Goldman, Marc Pégon, and Sylvia Sarfati. So the Aviles-Giga functional, it came from a model from mechanics, and variants come also from micromagnetism that we seen before. But here I will present another way to derive the Aviles-Giga functional. It has been made by some physicists, which works on pattern formation. So, so there is a lot of models which for describing pattern formation, and which describes some phenomena in physics or in biology, anything. And the main equation for pattern formation is the Swift-Bohenberg equation, which is an equation with a lot of parameters, and it's time-dependent equations. But so you can have periodic in time solutions. You can have dynamics with chaos, but everything such things are too complicated for me. So here we skip. We stay on descriptions of parameters of the equations that corresponds to descriptions of two-dimensional stripe patterns, and where the evolution equation, so the Swift-Bohenberg equation, as a Lyapunov function. It's a variational situation. So it's very particular. So we want to represent something like this. So it's a stripes, the domain with stripes, and we want to consider stripes which are with a smoothly varying period and smoothly varying direction. But the approximate period tends to be a small parameter eta. And okay, so this is here is described by a function which takes only two values, 1 and 0, which are corresponds to black and white. Okay, and we assume that the period is small, so at some point you will not want to see this, but just the directions of the stripes. Okay, and so the model, the first model is to describe the stripes through a phase. So we are given a profile P, which is a function from R to R, and the stripes, the pattern is described as a function f of x, is described as a function phi of the phase divided by theta. So, so pi gives the shape of the periodic changes, and here the period is eta. You want a period eta, so this means that you choose P to be of one periodic profile. So when you are left with the constraint that the gradient of theta should be also almost of norm 1 in the domain, if you want this to be of a period almost theta. So theta, gradient of theta is curve free, and we will consider rather the variable u, which is the gradient of theta. So gradient. So the conditions are the gradient, the curve of u is 0, and u should be of norm 1 pointwise. So here are the same stripes as before, and here the corresponding arrows, corresponding vector field. Okay. So the physicists, so this is one big group of physicists, they propose the cross-newell model, which is this one, function of theta. So they want to consider this energy. So the flow tends to optimize this energy. So if you recognize that this Laplacian of theta squared, and you see that this is this integral is just the integral of second order the Hessian matrix plus boundary terms, and I'm not interested in the boundary condition, then I just obtain the Aviles-Giga function. So I replace regular theta by u, and this is just the Aviles-Giga function. We have derived the Aviles-Giga function, so it's not interesting. Already studied. But so I skipped. And I recall something. So for the Aviles-Giga functional, as epsilon goes to 0, and for u in BV, the gamma limit is well known. So u is a function with BV with norm 1, it's curl free, and it has a jump set, and the energy is cube, the integral of the jump set of the cube of the jump. Okay, divided by 6. Okay. Okay. So if I consider, okay, so this is for u in BV, but if I consider the set of function u in L1, or vector field u in L1, whose gamma limit is finite, then it's much larger than BV. So it contains a curl-free BV vector field, which value, which magnitude 1, but it's strictly contained the function of with value in S1, which are curl-free. In fact, the result of Giraldin and Lamy says that you have something which is a Bezoff space. It's the intersection of the Bezoff space and the constraint. But I want to insist here that since the convergence, since the curl is linear, so the differential operator is linear, and at the limit you still have this. Okay. So I repeat the big picture of the what we expect, what we think that happened, and we send epsilon to 0 in the Aviles-Giga functional, so that up to extraction at the limit to obtain something like this, which is something which is you may have a vortex here, and you have otherwise you are curl free, and you have line discontinuities, and through the line discontinuities you are still curl free. That with the tangential component of the jump doesn't change. So there is no jump of the tangential component. So this is what I call the curl free jump. So this is what is expected. So if I come back to the stripes, here is what is a line singularity. What is one-dimensional singularities? Here it's straight line, but you have just a jump in the directions of the stripes. Okay. And so the question is about the cost of such a jump when epsilon goes to 0. So here I made a mistake. So x1 is in the direction. In the next slide, I switch. Okay. So x1 is the next direction. So I'm looking for the cost of transition from this to this. And I assume that there is no variation whatsoever. It's very slow in this direction. So I assume that the variation is scale epsilon is very close here, and there is no variation along the x2 axis, which is this one. So I define the 1D, the cost of the 1D transition between an angle phi and an angle minus phi, which correspond to u minus and u plus in the direction x1, which was the vertical direction previous slides. And it's easy to you assume that you have no variation in this direction. So in fact, the curl-free conditions Now it turns out that it's just that the second component does not change. Vector does not change. You have these conditions at the limit for the vector, and your Aviles-Giga energy per unit length is 1, and this is just a version of the Modica-Mortilla problem, so you can solve it exactly, and you find that the cost is cubic. So you have a cube. So this is what we expect. We have another type of singularities which have no energy. So they have no energy, and so there are vortices, and they are called target in the vocabulary of patterns. So it's a target. And you see that here, so now I introduce something new, is that here I choose something, a profile, which is in which one you cannot decide whether I'm going from theta is increasing in this direction or decreasing, because my profile is as a symmetry. So I'm a +1 on an interval of length 1/2, and 0 on an interval of length 1/2, and I continue again, and it's the same in both directions. If I reverse x in -x, I have the same. So of course I can change the arrows, and I don't see anything. So it's the same in the same pattern. Okay, and so sorry for epileptic people. So we have here we may have U-turns like this. The direction of the of U here, I may imagine it radiates from this point, and here I have a discontinuity here, where here it's upward and here it's downwards. But since I cannot distinguish between +u and -u, I may have this picture. So this is what proposed the physicists to just consider this as a possible acceptable patterns. So this is also, you can see it has a 1R discrimination on mechanics. So here I would call it a U-turn. And I can represent it using a vector field. Of course, I can use this vector field to represent my pattern. But the problem is that this vector field here has a jump. And so if my theory is correct, this has a cost. But in practice, there is no jump. So there should not be a cost. There should not have a cost. So we just identify U and -u. So I just erase the arrow. This is the model proposed by Ercolani and okay, but they just make this identification and then make computation in particular cases, but they do not build a theory, mathematical theory. So we try to do this. So a way to identify U and -u is to consider the tensor product. So I call this P. It's a topological space of tensor product with U in R2, and it's a plane. You just consider alpha plane, and you just take back. You obtain a cone. And the cone is a plane. Yes. Yes. Okay, and I have to decide. The problem is that I have to decide what is a curl-free vector field in this situation. And here it's more complicated. So I create an operator which is curl bar. Okay, and don't look at the definition. Look at the first line. Curl bar is defined as two vectors in R2. So for a vector, u curl of u is just a scalar. Here I have, it's a 2x2 matrix, but I have too much information in this thing. So it's just for symmetries I keep all this, but so you can forget about the symmetry, but the definition, but you can see that this is, so you have partial derivatives, of course, but this is also depends on V, so this is non-linear. Okay, so the curl is non-linear. Okay, but the good news is that we build the curl bar so that if I write V as a real product of tensor product of a vector field which is in H1, then my curl bar is something times the curl. Okay, and it vanishes if and only if the curl of U vanishes. So this gives me a meaning to curl-free non-oriented vector fields. Okay. The purpose is just to define something. To have a definition, a way to say this is a curl-free non-oriented vector. Okay, and then I define, so I can replace in the energy, and then I look the Aviles-Giga energy. I can write it like this. When V is of this form, is U tensor U, then this is exactly the yeah.
So what's the curl for that topological U effect?
0.
Okay, so you don't see, because right, that's like so it's not H1, right? The U is not H1, so you can still give a meaning and it's 0 there.
No, you don't use H1. It's your W11 is okay. And okay, W11, and you assume that this is bounded. So. But if you want, you can divide also. You can divide by the norm. This is a choice. There are several choices. There is no canonical way of choosing this operator. Just there are. But it has all the desired properties. If you can choose for vortex, you don't see anything. So okay, so I defined this energy, and now I want to find the possible gamma limit. What could be the gamma limit of this problem? And I say, okay. So I call RP1, so the projective circle corresponds to the vector with the vector fields with norm 1 vector fields. Okay, so it's corresponds to the circle. So it's a circle.
Okay. So in the energy you divide by the length of V.
Yeah. No, because in gradient of V square, sorry. In gradient of V square, you have U square.
But U is almost like 1 if you.
Yes, but yeah. But I want this identity. So it's even for U far from norm 1. I just replaced just okay. But of course you can get rid of this. It does not change. So now, what is the natural space? Natural space we are looking for limit object. So I will replace BV by SBV. So special function with values in this projected within circle. I want the absolutely continuous part of the curve to be 0. So I want something which is curve free. And then I have the problem of the jumps. Okay, and on jumps, I have this condition for if v is given by u plus and u minus on both sides of the jump, I have u plus minus u minus dot this is equals to 0 in the Aviles-Giga model. Okay, but here I can choose either u plus or or minus u plus, and u minus or minus u minus, because both things are have been identified. So when I see a jump, it's admissible if one of these two conditions is satisfied, or plus or minus. Okay.
Sorry, I'm coming back to the question. So when you have that is curl free, a v that is u wedge u, u tensor u. So saying that curl of v is 0, is it equivalent by saying curl of u is 0?
Yes.
Okay.
If v is u tensor u, yes. But I want to consider things where v is not a tensor product of something which is with sufficient regularity.
Right, but if we know that if v is bv, then you have a u that is bv. And you can define
you need to have rank 1. It doesn't consider rank 1 matrices. It's symmetric matrices.
No, I have a lifting.
Yeah, if v is
SBV, you have a lifting which is BV, you're right. Yes, but I want to take a square root. I will not have this.
Just to understand,
No,
so in terms of u, so what do you have there?
Yes, but okay, not all lifting will satisfy this. Okay. But, I need a lifting which satisfies this. Sometimes, so you will create jumps,
right? But
between plus u and minus u.
Yes,
but not necessarily along something which is curl free. Okay. You're right, but I don't want to consider this. For me, this is for me.
Yeah, that's
okay. I don't want to consider this. If you add this, if you say this is of energy 0, then okay, you're right. But I do not consider this.
Okay, so that's not admissible for your finite.
Yes, it's not, but in fact, it will not change much. Okay, then I guess that the energy will be a line energy like before, with the same cubic const, but the jump is u plus or minus u minus, and this plus or minus is the same here. Okay, corresponds to a real. I made a choice locally, and this I have to consider the energy, compute the energy corresponding to this choice. Okay, so this is a naive way, and in fact, this gives an upper bound for the energy. We can build something which gamma limit. This is an upper bound for the gamma limit. But okay, the main part of the rest of my talk, I want to discuss about this. In fact, I want to say that I want to show you that this is not true for large jumps. This is not the good formula. But to justify the distribution, sorry. So here is an example of a vector field. So you told, okay. So this is an admissible admissible configuration, but you see here, if this points right, I put a vector on the right, then here I will have to put a vector up. And here, if it points right, then I would have to put the vector here down, so the arrow pointing down. So I have I had to, if I want to as Radu proposed, to get a lifting from this non-oriented situation, given orientation, so this is a mess. Because there is a difference there, and if I make this difference between the points there smaller and smaller, then I will have arbitrarily large number of rotations. So it's still in BV, but very large.
Yeah, but the best constant is 2.
Yes, but you will not satisfy my constraint. What? Hmm? Remove my t-shirt. No, that's it. Yes, I would also want to. Okay, so well, before going to further, I want to justify why we are looking for the gamma limit, because okay, we have a compactness result list when I consider an equibonded sequence of configurations with equibonded energies, and up to extraction in L1. I have conversion in L1 towards something which values in the P, and in fact V is, since the convergence is in L1, I have a strong convergence almost everywhere. I have point-wide convergence almost everywhere, and V is in RP1. Okay. But in general, it's not curl-bar free. So this is why I'm insisted. We lost in the limit. We lost the differential condition, and in fact, one part of the energy can be used to violate the constraint. And okay, this comes as a surprise, but it's not so much a surprise because our operator is not linear, so it doesn't pass to the limit in the sense of distribution. Okay, and we also have a very good description of the zero limit states. So when I assume furthermore that the energy goes to 0, then outside the locally finite set, so I have some points, and outside this set, V is a locally Lipschitz continuous. And in fact, so I will make a picture. In fact, in this region, so you have V, which is like this, it's Lipschitz, and you have the same thing, it's constant along the line, like this. In this domain, you have this. So it's Lipschitz continuous and constant along its own direction. Okay, and if you take x naught point in the singular set, and you take a ball center in x naught which does not meet the singular set except at x naught, then you have two possible situations. So either you are in this situation when you have a target, or you have a U-turn. You have a U-turn, and so in this side you have a U-turn, and the other side this is Lipschitz continuous. Okay. So this is a zero energy limit. So now we want to know what happens when the energy is not zero, and we want to compute the cost of a jumps. We expect to have jumps. So to compute the cost of a jump, so I note E phi or will be U plus and U minus, E phi and E minus phi. So it's a norm one vector with angle phi with respect to the horizontal line, and phi is between 0 and pi over 2. So okay, the situation is this one. Okay. So I have this u minus there and u plus there, and I want to go from there to there at the minimal cost. And I consider periodic conditions with period L here, and here is infinite. I want to guess what is the best way to go from there. So I have a first way is to go with a Montica Mortola style in 1D transition. So I already have a lower upper bound. Okay, so I consider all the possible. So we skip this, but I consider all the possible these natural objects that I consider. So things which are I send epsilon to 0 already. So these things with lines, and the cost of a line will be the cost of the 1D transition of this line. But I'm wondering whether if I can arrange 1D transitions to get a better cost, to decrease the cost. Okay, so this is my first bound. It's given by the 1D transition. It's 1/6 divided by the cube of multiplied by the cube of the jump, and this is in terms of phi. This is this. Okay, so and I consider all the, and I will give first a lower bound using calibration. So I use calibration. So I consider a triplet of a free jump. So I go from u minus to u plus, and I this condition. So there is no jump in the direction orthogonal to nu. So nu is a normal condition, and this is a tangent to the jump. And I consider the calibration. These are the entropies of the preceding in this situation. But I ask something more. I ask that my jump is smaller. The jump in direction u is smaller than the cost of 1D transition. Okay. And okay, and if V is smooth and curl bar free, then I no the divergence is nothing. So when I compute the divergence, I will only see the divergence. I will only see the jump set, and on the jump set, the divergence is just the jump of but the direction of the jump. Okay. For every calibration, we have the cost to go from u minus to u plus is bounded by the jump of phi between the bottom value and the upper value. Dot E2 is the vertical direction. Okay. Well, I don't explain you the computation of the calibrations, just give you this. So we have a first lower bound which is given by this formula. You find a calibration which works, and it's given by this formula. So we have two formulas for a moment. We have a formula for the lower bound. So the cost is at least given by this. So here it's pi over 2, and here is 0. So here is pi over 3. And so from 0, and here is the upper bound, which is given by the 1D transition. And from 0 to pi over 6, it's a rematch. So I cannot do better than the 1D transition. Here we see that I have some room, and I expect here to be better because this, in fact, for pi over 2, this corresponds to a jump between this and this. and this should be 0. Okay. So this point is much more reasonable than this one. Okay, and we don't have too much to see because the physicists propose zippers constructions. And in fact, they obtained it by numerical simulations. And where they replace a jump by, here you see, so it goes to U plus and U minus is hidden. So you have a period here. Here you have a alpha vortex, and here it repeats here. And here you have a region where it's constant. So the direction is constant. I write the arrows with two different directions, but here there is no. And okay, so you have this interaction between this. So there is no jump here, there is no jump here. So the jumps are only on one period, the jumps are only on this part, this parabola, and this part, which is a hyperbola. This thing. And you can compute the cost, and you get here you get a better an upper bound which goes to 0, at least. But here it's not very good for small. Okay. But in fact, they are not optimal. These zippers, we found a way to improve the zippers by noticing that in the zippers you have. In the construction here, you have angles which are more than pi/6. So it's not a good idea because we only know that angles smaller than pi/6 are 1D optimal. So we modify the construction in this region, and we put a triangle there, where we here, at the point where the angle is exactly pi/6, we stop the vortex and we replace it by something which is constant with the same angle. And here we have 3 branches of jumps, which are pi/6, pi/6. Okay, and this lowers so this works only for large angles. So cosinus of pi should be smaller than 1/√3. We have another construction for smaller angles between pi/6. So the modifications of the interaction is okay. So this constant part joins the hyperbola. You can compute, and then you have you are happy, and at the same time very disappointed because it does not match. It does not match the lower bound and the upper bound. And you see, you look at the difference. So here you have 0.5. And when you look at the difference, it's of order of 2%, 2 divided by 100. So it's quite small. But we can improve the lower bound. Okay, so I will not explain. The lower bound, I obtained it by a calibration. But I was looking for a calibration which fits all possible cases. But when I think about calibration which fits a specific angle, specific jump, then we found a calibration which shows that this one precisely, where the cosine of phi is 1/√3, this one is optimal. The construction is optimal. This is where the point where both constructions the join. And we have another result that there is no calibration that can prove that the other are optimal. Does not mean that they are not optimal, but the calibration method is not optimal. But this calibration is like you looking at the convex at the dual problem, but you're looking at the dual problem of non-convex problem. So you may have a gap. It's not surprising. I don't expect to. Okay, but okay, at least we have this one, which is okay. Okay, so this is what I just said. So okay. But we have another situation, which is a very surprising situation, which we discovered that we can have non-curve-free jumps. So non-curve-free here, at the limit, I have a vertical field at plus infinity, and minus infinity, I have a horizontal field, vector field. And I build something periodic with made of so I have here I have pieces of vortex, pieces of vortex, and you have the same triangles as before, and you have artificial jumps which are no cost here between plus and minus E1. Okay. And this has a finite cost. And at the limit, when I send the L period to 0, I obtain something which is I obtain this limit vector field of direction, which is clearly not curve free, not curve bar free. Okay. And this complicates a lot. So in general, I can make a jump in any direction in this way. So given U minus and U plus, I have an admissible jump direction of the jump between U minus and U plus. So the direction of the interface is here. And if I change U minus to minus U minus, the direction of the interface is now orthogonal to the preceding one. So I have two orthogonal directions, and two orthogonal directions, I can do two vectors, two orthogonal vectors, non-zero, they span R2. So I can make, for example, here I will produce the horizontal jump. So I repeat the sawtooth construction, and so you have to imagine. So I have a scale for the sawtooth construction, and I have another scale here with zippers. Here, smaller scale.
By the way, on the zipper, you go in one direction. Always you do 1D transitions, yeah?
Yeah.
Each one you do 1D, and then you have to match in some sense, yeah?
Yeah. Yeah. So here I have zippers, and if I come back to zippers, sorry, I come back to zippers. Here I have zippers, but here I have 1D transitions. If I come back, if I let epsilon positive, so I have three different scales. Next, but okay, now if I take any V, which is BV, with value in RP1, I divide in hexagons because I like this. It's not important. You divide in hexagons your domain, and you approximate V by a constant on each one, and you have a piecewise constant domain, and each you have to deal with these jumps. We replace these jumps by sawtooth jump. You approximate them by sawtooth jump, and then you put zippers, and then okay, and you can approximate any BV function. Okay, so in fact, what happens that we have proven that the limit, the gamma limit for BV is controlled by the BV norm. So the measure of gradient of V. So we can admit contour anything, but the most important thing is that we have lost the differential constraint. So since for the Aviles-Giga problem, we still do not know do not know how to prove that what we expect to be the gamma limit is the gamma limit. In this case, it's worse. So we want to try. And the conjecture is now that you have something like this for the gamma limit should be an integral of something which lives on a jump set, maybe, if we are able to define a jump set. But we have something which is depends on the curve in the diffuse part. The diffuse part of the curve.
But
the curl is not zero.
But you know it's a measure. That the limit stays a measure.
What? Yes, yes, gamma limit should be a measure. Yes.
No, for the curl.
Yes. Yes, because you control it by the.
Oh, it's a BV. Okay.
You control it by the energy. And yes, I assume that. Okay. Okay. For more than BV, I don't know. I don't know what is the correct admissible objects in the limit which have a finite gamma limit. I don't know.
So you didn't analyze the Young measure?
No. Okay, but what we know is that this constant will be smaller than plus minus d minus, but if the jump is curl free, this is a cube there. Really complicated function anyway. Okay, I have finished. Thank you for.